All right, so today we've looked at sample means. So look at comparing the mean of the sample to the population. This is what this confidence interval bit is about. Um, Essentially, what is it? It's about what confidence have you got that the mean that you get from your sample is related to the population mean. And so why do we do this? As it says there in that sentence there, it might not be possible or practical to determine a mean for the whole population. Because if it's a big population, it takes a long time to get the information, and then also takes a long time to then process that information. So we use the sample mean to estimate the population mean. All right. And so if we use just a single value, so we took one sample and we just used that, then we call that a point estimate. However, commonly what we do is we use a range. So it's related to this point estimate, but rather than just saying it's 5, we'll say it's between 3.5 and 7 or something like that. So commonly a range is used to state where the sample mean will lie with a high level of confidence. So that's what we call a confidence interval. So how confident are we that the actual mean of the population is going to lie in that range that we've got. All right, so an example, and this is not the only range that you can do, but often they're written in this form. So an example of that. So the population mean will be in this interval. So this is the sample mean that we've found out, sample mean. And so this number 1.96 times standard deviation over the square root of the size of the sample, right? So this thing here if you like, is the sample standard deviation. All right, so the population mean is going to, if you take 1.96 times sigma over root n, whatever that number is, if you take that away from the sample mean and then you add it to the sample mean, that gives you a range of values that the population mean will lie in. Now this particular number here, the 1.96, what that relates to is what we call the 95% confidence interval. So in other words, on 95% of occasions, the actual population mean will lie in this range that you get from your sample. All right, so X bar is the sample mean, sigma is the population standard deviation, and n is your sample size. All right, so here's an example from your textbook. So find an approximate 95% confidence interval for the mean IQ of Year 12 mathematics students. If we select a random sample of 100 students and find the sample mean to be 108.6 and assume the standard deviation for this population is 15. All right, so we're talking about here, as you can see, Year 12 mathematics students in Australia, that's a lot of students, all right? So here we're using a sample of 100 to find out. All right, so n is equal to 100. X bar, we've been told, is 108.6, and so our standard deviation is 15. So our 95% confidence intervals are the one we did before, X bar minus 1.96 times the standard deviation on root n. And so our population mean is in between that and sample mean plus 1.96 times standard deviation on root n. All right, so if we put those numbers in, 108.6, take away 1.96 times 15 over root 100. So the population mean 108.6 plus 15 on root 100. And then that's where we get our calculator out, put all of this stuff in our calculator. And when we do, the one on the left there, the minus comes out to 105.66 and 111.54. All right. So the mean IQ of mathematics students in Australia, if you then relate to that population, then the mean IQ of that population would be somewhere between 105.66 and 111.54, and we could state that with 95% confidence that that is the case. And of course, IQ of the whole population rather than your just mathematics students, year 12, is out of 100. So of course, as we realise, mathematics students are more intelligent, which is not really surprising at all, because mathematics is an excellent pursuit, of course. All right, so your calculator can do this stuff there. I just waffled on with some controversial stuff there, but anyway. So our calculator can do this. So if we go to our calculator and we go, okay, let's go to our menu, go to our statistics, and then we're going to calculate something. What are we going to calculate? We're going to calculate an interval, all right? So we're after a confidence interval. So we're after an interval. There we are. What do we want? And type interval, yes. What do we got? There's a bunch of stuff here. One sample is the one that we want there. And we want variable. All right, then we go next. All right, our C level, so our confidence level. And you can click on help here if you want, and it's going to, all right, take that up and it tells you what you want. And the confidence level is between 0 and 1. So we need to be, we want 95, so 0.95. Then population standard deviation. We were told the population standard deviation there was 15. This is the mean of our sample. Okay, see, it's telling us there. So if you forget what it is, you can go there, 108.5, no, 0.6. And the number in our sample, we had 100 in our sample. And we go next, and there we go. So our confidence interval between 105.66 and 111.54. All right, so that's how our calculator would calculate it for us. And did I put those steps there? There we go. I did put those steps there. All right, so what I just did is there. All right, so what does this mean? All right, as it says there, I already mentioned this, the population mean will be in this range on 95% of occasions. All right, so if it's in this range on 95% of occasions, then that leads to this next bit, margin of error. So on 5% of occasions, It's not, so there's going to be an error there. So it's what we call about the margin of error. All right, so if we take a different sample size, say 400, then for this particular thing above, if instead of 100 we take 400, then here's our confidence interval. Our confidence interval for that is this 107 to 111. So that interval has come in. So it's now narrow. It was 105 to 111-ish. And now it's into 107, 110. So it's now a narrow interval. So because it's in a narrower interval, because of that higher sample size, okay? Remember, the bigger the samples, the closer things are going to be to the actual. All right, so that's the sample size. So if that interval is narrower, then what that means is there's a smaller margin of error. All right. So for the 95% confidence interval for the mean, the margin of error is that factor, the 1.96 times the standard deviation over the square root of the sample size. All right, so that, remember, that was the bit we did, the plus or minus bit, all the way up here. Don't get dizzy as I go all the way up. All right, here it is. So that's the factor there. That's the one we added there and we subtracted there to get our interval. So the smaller that is, the smaller the margin of error. All right, so in the previous example where we had a sample of 100, when we put that in there, it's 2.94. So we expect an error of 2.94 in the estimate of the mean. All right, so we estimated the mean as 108 or whatever it is. Well, let me double check. 108.6 is what we estimated the mean for, but there's an error of 2.94 plus or minus in that. All right, now what do we got? So we can rearrange this formula to determine the sample size necessary to give a 90% confidence interval for the margin of error. So that's just taking this. So if we want a particular margin of error, this is 2.94, but if we want some other value for it to be, say we wanted the margin of error to be 1.5. So if we rearrange this formula here, we get this one here. And so we can say, well, I want a margin error of a particular size, put it into this formula, and this tells us how big our sample needs to be. So in the previous example, if we want a margin of error of 1.5, for example, then we would need to say, okay, so n then has got to be 1.96 times 15 was that standard deviation. We want 1.5 to be our margin of error. Square that, stick that into your calculator, and you get 384.16. All right, so that then means we need to have a sample size. We need to have at least 385 people to get that margin of error. All right, so we can change our confidence level. And so in general, a C% confidence level, the one we used is the 95%. It's this here. This is the thing that it is. And this K in here, this K, this number, and for 95%, that K was 1.96. So if you want a different percentage, then that K number will be a different number. And so if we want to find K, we can use our calculator, and here's the steps. All right, so say for example we want to 99% confidence, then this is what we would use. So let's go to the calculator. And here's our calculator. We need to go back to my menu. Let's go to stats, calculate. Now this time we're using the inverse distribution. All right, so we're going from that percentage back to something else, whereas in the previously we've had our values, our data, and then we've gone to that percentage. Now we're going back the other way. And so inverse distribution, and then we want inverse normal. There's a few different ones. We want the inverse normal. And then we go next. And then it asks us about did I choose the right one? Yes, I did. Inverse distribution. Then it asks about the tail setting. We just leave that there. At center, it's left, right, or whatever, but we go at center. So all that means is we want it symmetrical. And so probability, what probability are we after? If we want a 99% probability, so we've got to put it in as, again, you can go help. Again, it's between 0 and 1, so if we want 99, it's 0.99. And then we go next. And so this number here is the one that we're interested in, and we don't need to worry so much about our plus or minus bit because that's in part of the formula, but it's the if we go to 2 decimal places, it's the 2.58 bit that we're interested in. All right, so K for that, so if we want 99% confidence interval, K would be 2.58 for 99%. All right, and so the confidence interval would then be between some x bar minus 2.58 times still standard deviation and the number of sample size, I should say, and the mean plus that number, and that's our margin for error, of course, 2.58 times sigma over root n. All right, so in the example that we've used before, then our confidence interval would be 1.108.6 minus 2.58 times sigma 15 on root 100, and the population mean is between there and 108.6 plus 2.58 times 15 on root 100 again. And then if you stick those things in your calculator, here you get 104.74, and at the other end you get 112.46. So you can see that interval is wider than it was for the 95%, all right, because we need to go wider so that we get more of the things in, all right, because remember the whole population is 100%, and so to get all of that in, we've got to go wider and wider. All right, so the confidence interval for 99% confidence is 104.74 to 112.46, somewhere in that interval. All right, so that's the theory in behind confidence intervals. So the interval between which you can say, based on your sample data and your sample mean, based on that sample mean, the actual population mean will lie in this range on a certain percentage of occasions. And so you can have a look at that in a number of different ways. You can, to become more accurate, you can change your margin of error, and so you can then figure out how big a sample you need to take, and so on. All right, so I'll leave you with that. If there's things you need clarifying in there, make sure you ask us some help. And as always, have fun.